I guess last week I asked you guys to watch the video clips related to generative adversarial networks. So let me review or recap what GAN or GAN briefly. So the first one is the motivation is that all the either supervised or unsupervised learning it was the discriminative models. So whenever we have some data set, we have to discriminate whether this is 1 or 0s, those kind of the task that we had. And unsupervised learning is that we want to generate something instead of having the discriminative task. Okay, so here now you already know, you watch this, so it's we call it latent space. Remember in autoencoder we have low dimensional structures. You have small number of neurons, and we call this latent space, or it's latent code, whatever we have, or sometimes we call it is noise, because in most of the case we're gonna randomly generate the values in the latent space typically from the Gaussian distributions. So we call it is kind of, if we normalize it, it's kind of we can treat it as noise, but it's not noise. So randomly select the values in the latent space. In many cases, the latent space we're gonna have Gaussian distributions, and through the generative models, we want to generate something like real looking the images or whatever. So now we have to talk about the distributions first, and the idea is that in many cases in statistics and the probabilities, these are kind of the probability distributions. If you know the distributions, then we kind of say that we kind of know all the process, or we kind of know the systems or applications. But in the perspective of probabilities, in many cases we assume that the probability distribution is none in advance, right? But in statistics, we assume that we have no idea about the probability distributions. All we have is data. So in the title is the probability density estimations from the data, right? So starting from the data set, if given the data set, we want to estimate probability density functions. There are many ways that in the probability density estimations, but in here we want to do using the deep neural networks for the probability density estimation task. So let me see. So the question is, how can we represent or how can make the deep learning models to represent probability density functions? That was the motivation that we have. Okay? From the given data set. So the idea is that there's no way that we can represent probability density functions in deep learning using deep learning model. But if you look here, it's transformations. What do you mean by transformation is that we want to have some kind of transformation from or via a neural net or deep learning models. What do you mean by that? That suppose we have input probability density functions. Since this is input, we probably in many cases we're going to assume that it's Gaussians. because it's input. So starting from the Gaussian distributions, this is our assumptions, or it's none. Because we assume that it's Gaussian distributions, it's none, like this. But the true probability density functions to represent the data set that we have, it doesn't have to be Gaussian distribution. It could be any arbitrary. That's the output distributions, but we don't know. So we want to estimate arbitrary probability density functions. Okay, to represent true distributions for our given data set. Okay, and the key idea is that from none, usually it's Gaussian distributions, from that Gaussian distribution to any arbitrary distributions, it will be some kind of mappings or transformations. This one is deterministic. We want to teach, or we want to have neural net to learn this kind of transformations. Okay? Actually, we're not gonna ask deep learning models to learn the output probability density functions. That's not. We're going to have this one from deep learning models. That's what we want to do. Okay. So it's known that from Gaussian distribution we can make some kind of transformations to represent any probability density function. Okay, that's none. So we want to replace that transformations via neural net or artificial neural net or deep learning models. So please remember that neural net does not generate probability density distributions, but it maps from non-distribution to target distribution. Okay, there will be input and output. The input, probably you could say, it could be uniform distribution, it could be Gaussian distribution. Right? The target distribution, so that's we don't know, and we want to estimate it to represent the true distributions of the given data set. That's what we want to do. So that's the key concept. Okay. So to illustrate it, so in higher dimensions, so suppose it's in latent space. In that figures, it could be like it represents 2D space. It's a unit Gaussian distribution, and here is transformations. That's transformations. We don't know. You can think of it as a corner. Instead of we define for user to define, hey, I want to do certain transformations. Assume that we have no prior knowledge. We want to learn that transformation from the data set. Okay, so if that's the true data distributions, we wanna kind of approximate it. And in order to do that, what we need to do is that somehow we need to define some kind of loss between the generative distributions and true data distributions. How can you define the loss between like two different probably dense distributions? That's kind of things that we have to think about it. Okay? So again, let me tell you that starting from, you can say starting from non-Gaussian distribution. And there are many ways. The GAN is not the unique. There's the unique one, but say, like I said, here, how can you define the loss functions and how can you define the transformations? And the key idea is that in generative modelings, we like to train the networks that models the distributions. But GAN do not work with explicit density functions. That's the key idea. Probably it's difficult to get the exact meaning of explicit density functions. Okay. And the key idea is that if what we want to do is that we want to make the generative distributions as close to the true data distributions, right? As much as possible. So the idea is that if you sample the data from this one, and we can sample the data from the generated distributions, or we can just sample like from the training data set. Right? If these two are similar enough, probably we're not going to tell whether the sampled data set is from the generated distributions or true distributions. That was the key idea. And we call it discriminator. So the idea behind GAN is that we train two different networks. The first one is generator. The later one is discriminator. For generator, we want to try to make or produce like realistic looking sampled data. And for in other side, the discriminator try to distinguish, to make the difference between the real and fake data set. So they are competing each other. Okay. Eventually, what we want to do, right? We want to find out the transformations using these two like competing training process. That makes sense? So again, I think I mentioned like autoencoder is some kind of the key structures that I like. So if you remember, it was starting from dimension reduction. It's starting from to recover the input data set, reconstruct, and in that process, we achieve that dimension reductions. And this part, and later part, we can treat it as a generative models. So starting from the autoencoder structures and the decoder part, we can treat it as a generator. So it was the latent space, right? It was the output in the sense of autoencoder. And now remember the output from the autoencoder, the quality of the quality of a reconstructed image is not as good as, right? It's not that good. So we want to add another neural network. We call it discriminator. So you can think of it as a decoder from the autoencoder, but here it's gonna work as a discriminator. For this discriminator, it takes the input from generated one, which is fake, or we can take from real data set. Okay, and for discriminator, they have to tell whether this is fake or real. If these two are way different, probably it's easy to tell for discriminator, hey, this is real, this is fake. Right? But if these two it's difficult to tell the difference. Probably discriminator say, I'm not sure about whether this is real or this is fake. So if you think that as we put it sigmoid at the end, probably the value is out of the sigmoid function is like half and half. So it's like we are not sure whether this is fake or real. So that's the key concept or key idea of GAN. Right? So let me tell you again, we have two neural nets, and these two are competing each other. The generator trying to generate from latent space or from non-Gaussian distribution or from I would say Gaussian noise, trying to make as real as possible. But on the other side, for discriminator side, trying to tell, hey, this is from, we know that I'm for sure that I know this is real or this is fake. Right? So we have two different tasks for two different neural nets and competing. Throughout this process, and eventually we're hoping that the generator trying to make or produce or generate like a real looking fake data set. That make sense? So I think in the recorded video lectures I use these examples to say that. So let me show you. The first one is from discriminator perspective. So think about it now. I'm a discriminator. Okay. So this real image. For if I'm discriminator, so I'm gonna say this is 1. I will say 1 is real and 0 is fake. Right? Or if that's the generated image or data for discriminator, so you have to tell the discriminator say that this is fake or this is 0. Right? That's the way we're supposed to set the loss function. Now let's move on to generator perspective. From latent space, we generate it. It's a fake. After discriminator, so this one is generated and discriminator. from generator perspective, this one should be fake or real. For generator, it should be real, right? So it should be close to 1. For generator, not discriminator. That's all we need to know. And the next step is that just write a code to like define the loss functions and how to optimize or train it, the networks. And how do you define it? Let me see. So let me see. So if that's the define the loss functions, let me see. I wanna for discriminator, I wanna maximize it. So for discriminator, let me explain it with this one. Let me move on to. So I will okay. So that's the basic concept of that, and I'm gonna explain it again. So using the MNIST data set, how to implement it. So I'm gonna use these networks. We have two, and this one is generator, and the other one is discriminator. And again, it's a MNIST data set, so it's a 20 by 28. So that's why we have the input layers for discriminator. It's kind of the fully connected layers. So its number of is 784. And since we have only like is real and fake, we have 1 neuron. If that's the one-hot encodings, probably we might have 2 neurons, but it's okay. And for generator, I assume that we have 100 neurons. That means I have Gaussian distributions in 100 dimensional space. Okay. Here, I'm not sure whether it's 100 or 10 or 50, which one is good. I'm just randomly choose. Okay. And for generator, let me see. We have this is generator, and input data is 100, and the hidden is 256, and the output is 784. That's the. And we have to do sigmoid functions. And that means the output here is all the values is range from 0 to 1. So I guess the MNIST data set here is I use the normalized MNIST data set. For discriminator, let me see, we have to flatten the inputs from input for the MNIST data set. So we have 784, and we have 256 hidden layers, and the output here. Again, we add the sigmoid functions to tag whether this is fake or real. Now we have to combine them together, because we start from two separate neural net, right? So we have to combine them. So how do you combine? And for generate, let me see. Combined inputs, we add that in generator is generated, and discriminator, we add the generated and combined outputs. We combine them together here. The input is combined inputs, and the output is combined outputs. And probably what you're supposed to do is that just looking at the pictures and to provide the code and trying to get familiarized with them together. and 2 for here, because we have to train discriminators and generator, like so. In order to train the discriminator, we have to fix all the values or weights for. So let me say it again. We have two networks, and we train this one first, and we have to fix all the values, and we have to make all non-trainable. And when you train this guy, and we have to make this or is non-trainable, is untrainable, right? So that's kind of thing that we need. And this is kind of, I mean, at least you have to spend some time to think about for here how to define the loss function. How to define the loss functions. So let's think about the discriminator perspective. For discriminator, if you have real images, you have to say for discriminator has to say it's real, right? And for generated images, discriminator has to say this is fake, right? And we have two, like, either cases. So that's the loss functions for the related to discriminator. And let's move on to, let's see, the loss functions. Let me see. So, and loss functions for generator, and starting from the noise, right? From the noise from the latent space. I mean, if you don't like noise, you can think of it as a sample the data from the Gaussian distributions. If you don't like the noise, the concept of noise, or the name of noise. If that's noise, for generator perspective, let me say that again. For generator perspective, it's from noise, so the output of generator it's a fake, but it's a faked image, and right after the discriminator, we have to fake this discriminator say this is real. For generator perspective. Does it make sense? That's how we define the loss functions for generator. Okay? And that's how we train them. We're hoping that all things have no issues. And once we're done with the training, so again, the purpose of GAN is to generate real-looking fake data set. So now we don't need discriminator anymore. We have all the weights and bias for the generator, and we just randomly, remember in the autoencoder, in the latent space, we can randomly sampling, right? We did the forward propagations for decoders, so we can make all the generated data or images as many as possible. That's what exactly we can do the same thing here in the generator as well. So again, we don't need discriminator anymore once we're done with the training process. Okay. Later on probably I have another topic which is like the anomaly detections. Probably we're gonna use a discriminator as well. But in order to generate any fake data set, we don't need discriminator anymore once we're done with the training process. Okay? So that's kind of generated images that we have from if you execute it, they provide the code that I had that I provided, but the quality is not that good, right? Then the reason why is that it's going to take a lot of time. It's going to take a lot of time. So if we want to have better performance, then probably you have to have deeper networks, okay? if you wish. But I can say it's kind of, I'm not sure, maybe it's 5, I don't know. Maybe it's 0 or 9, I'm not sure. So that's all the stories that I have. I mean, for related to the GAN, and there are a lot of things that I can talk about. There are some like mode collapse issues, but I'm not gonna cover all the kind of things. So GAN, the thing is, the concept of GAN is really important, and generators and the discriminators and the kind of things. And let me see, what's the next? Here, for GAN is that, say, in latent space, I'm gonna randomly select it, right? Now we have generator, train the generator, and we'll make some kind of estimated values. If that's the image, probably we can reshape it and see. But the issue is that we have let's say for MNIST data set, we have no idea is that whether this number is going to generate digit 5 or 9 or whatever. Right? You can generate any numbers. Okay. So I want to generate, I want to generate like zeros. I want to generate 5. I want to generate digit of 8. In order to do that, we have to think about conditional GAN. That's kind of another very made a small modifications based on the GAN. So here's the motivation of conditional GAN. For unconditioned generative models, we have no control on what kind of data, the mode of data are being generated. We have no idea. So we want to generate fake samples with the specific conditions or specific characters, rather than the generic sample from unknown noise distribution. Here is 100 encodings. And I want to do, if I let the conditional GAN, say if this is another input, it's going to generate zeros, and all of them is going to randomly generate 1, things like that. That's what we want to do. So this is the structure that we have. So let me write it down. So we have discriminator, and here we have generator. So it's a X fake, you have X real, have some here, as you see, noise like GAN, and we from the random sampling from the noise, we feed that into generator. It's gonna generate some real looking fake. Okay, and for discriminator, we have to discriminate whether this is real or fake. And so that's the output. That's the structure of GAN. Now what I want to do, okay, so using the MNIST data set, say I want to tell to GAN, let's say generate digit 5, and I have another information which is class. Here probably we'll say class, or probably labeled, or conditions. Let the generator know. So this is condition that I want to generate. Okay. And generator is going to generate the fake data set with that specific the class. And discriminator we have to tell. Okay. Among like this from 0 to 9, I'm just focusing on like these 5. Don't worry about others. And also we have to let, when we pick the real data set from among the training data set, we have to only pick the 5, right? So that we can make fair comparison with the real 5 and fake 5 data, fake 5. So that's the conditional GAN from this baseline of GAN. So that conditions and model of additional information for better multimodal learnings. Okay, let me explain with that. So in this is the illustration that I have from normal distributions. That's kind of the latent space. If we have like, you can think of high dimensional space, but I visualize it in 2D space. For GAN, suppose I pick the noise or like from latent space, and generate says is 3, and if you pick another, say 6, okay, we have no control on the characters that I want to generate. But in conditional GAN, we can pick the values, or it could be different, but if from the latent space, even though we pick the same random number, say we made the condition on different class or different labels, then it's going to generate 1 and it's going to generate 3. Okay. So for in conditional GAN, for in this case, I'm explaining using the MNIST data set. So the digit that I'm going to generate, that the generator is going to produce, it really depends on the class or label. And in what we did in the latent space, say we pick the noise from the latent space. If we move, like, we don't know, I mean, just walk in the latent space, then probably like the generated digits probably, I don't know, like say it's kind of rotated and make thicker, you know what I mean? So there's some kind of, let me see. Here, the latent space only encodes the features such as width or angles, whatever. Because since we have another conditional informations, we don't have to teach in the latent space, doesn't have to learn in the label informations. Only thing is that the characteristics or behaviors, or whether this is width or angles, and whether it's rotated or tilted and things like that. Okay. And how do you implement it? The condition again. Here's let me see. I think this is older version of me. Let me show you. Go back to. If you go to our web page, teach deep learning models. And let me see here. And we have, so that's the materials that you're supposed to look at. So that's how we implement the condition again here. Probably I'm gonna update it to this guy. Okay. Let me go back to. So here what we have is that from digit 0s to 9, and as we train the networks, as you can see here, it gets better and better and better. And that's kind of we have. The bottom one is like, once we're done with the training, I mean, don't worry about the quality too much. I mean, we can make it better. But as you can see, in order to increase the accuracy of performance, you have to make more like deep layers, and it's gonna take a lot of time for training. So that's why I kind of stop in the middle. But the good thing is that now I have control on the conditions. I know, because I mean, I can generate the digit that I want. But GAN, I cannot. But conditional GAN, we are able to do it. So that's kind of the view you're supposed to already know related to GAN.